always moving at the cosmic speed limit built into the geometry of the universe. This speed does not come from the photon pushing itself or propelling forward. It comes from the nature of the field itself. The field guides the ripple along, carrying it with complete reliability, never altering its pace. It is as if the universe offers one specific speed at which energy can move through the electromagnetic field, and the photon simply follows that rule without hesitation. Even though its structure is not that of a solid object, a photon still carries information. It can carry color, which is linked to the energy of its ripple. It can carry direction, showing where it came from. It can carry the story of its birth, whether that birth was inside a star, a glowing ember, or an atom excited by an electric current. Everything it carries is contained not in an object, but in the behavior of the wave itself. It becomes a traveling signature, a whisper from one point in the universe to another. If you think again of the calm ocean, you might imagine that the smallest ripple has no meaning, but even a faint tremor can tell you something. It can reveal where the disturbance began, how strong it was, and what direction it is heading. In the same way, a photon contains just enough information to let you know how it was created and how much energy it brings. Its simplicity does not limit it, it defines it. The pulse remains whole throughout its journey, never breaking into pieces, never losing its identity, no matter how far it travels. When the photon encounters something that can absorb its energy, the ripple ends. The disturbance fades, the energy is passed along, perhaps warming your skin, perhaps triggering a chemical reaction in a leaf, perhaps creating a tiny electrical signal in your eye. In that moment, the photon itself vanishes completely. There is no leftover fragment, no cooling ember, no dying spark. The ripple stops, the field becomes calm again, and the photon's story concludes. It is a peaceful thought in a way. A photon begins as a disturbance, spends its life traveling gracefully through space, and ends by giving all of its energy to something else. The entire journey is one fluid motion. Nothing is wasted, nothing breaks, and nothing lingers. It arrives, it travels, and it disappears. If it could be aware of itself, it might not even think of this as an ending. It might see its story as complete the moment its energy finds a new home. Understanding a photon as a tiny pulse of the electromagnetic field turns light into something more than a beam or a ray. It becomes a delicate rhythm, a quiet shiver that the universe sends through its own fabric. It becomes a reminder that not everything that moves needs a physical body, and not everything that carries energy needs weight. The most fundamental messengers of the universe travel not as objects but as patterns, beautifully simple and endlessly subtle. And perhaps the most soothing part of this idea is how natural it becomes once you picture it clearly. A photon is not a glowing dot racing through the darkness. It is a gentle unfolding in a field that fills all of space, a momentary tremor carrying warmth and color through a quiet, invisible ocean. It is movement made pure, energy made elegant, and light expressed in its simplest form. Mass is one of those ideas that feels simple until you try to explain it. You pick up a stone and it feels heavy. You lift a feather and it feels light. You push a shopping cart and feel resistance. You push a wall and feel even more. In everyday life, mass shows up as weight, as effort, as a kind of reluctance objects have when you try to change what they are doing. Something with mass resists being moved if it is resting, and resists being stopped if it is already moving. It carries inertia, the quiet tendency to continue its current state unless something nudges it in a different direction. When you walk, every step is a conversation with mass. Your body pushes forward against the ground and the ground pushes back, allowing you to move. If you were weightless, the smallest push would send you drifting away like a balloon, unable to stop yourself easily. Mass anchors you. It gives you presence, solidity, and a sense of stability in the world. Now imagine something that has none of that. Something so light that it does not just feel easy to move. It cannot ever be at rest. It cannot sit still on a table. It cannot float lazily in a corner. It cannot slow down or pause for even a moment. That is what it means for a photon to have no mass. It is not just weightless in the everyday sense. It is free of the very property that ties objects to the rhythms of motion and stillness. To picture this, imagine trying to hold a ripple in your hand. You cannot. The moment you try to bring it close, it moves away. A ripple on water exists only through motion. The instant it stops travelling, it vanishes back into the stillness of the lake. A photon behaves in much the same way. It is a small pulse of energy in the electromagnetic field, and its existence is tied completely to movement. If it were to stop even briefly, it would no longer be a photon at all. It would simply cease to exist. Mass gives objects the ability to rest. Remove mass and the concept of resting disappears. A photon is born in motion and continues in motion until its journey ends, carrying energy from one place to another. It never needs to accelerate, because acceleration is something that applies to particles with mass. A photon begins its life already travelling at the fastest speed the universe allows, as if the cosmos itself whispers, "Go," and the photon obeys instantly and forever. This speed, the cosmic speed limit woven into the fabric of space-time, is not arbitrary. It is the speed at which ripples in the electromagnetic field naturally move. If you imagine dropping a pebble into a pond, the ripples glide outward at a speed determined by the properties of the water. They do not hesitate or negotiate. They simply follow the rules of the pond. The photon behaves the same way, travelling at a fixed pace set by the nature of the field it inhabits. It is almost poetic that a particle with no mass travels not just quickly, but at the absolute maximum speed any information or energy can achieve. Nothing slows it down, because nothing about it interacts with the world in a way that creates resistance. It does not collide with air molecules in the way a pebble would. It does not experience friction. It does not press against anything. It glides effortlessly, not because it is powerful, but because it is simple in a way that matter can never be. Consider the difference between pushing a heavy box across the floor and sliding a single sheet of paper through the air. The box grips the ground, resists movement, and needs constant effort to budge. The paper floats freely, carried by the slightest breeze. Now imagine something even lighter than the paper, something so light that the concept of pushing no longer applies. This is the world a photon lives in, a world without weight, without friction, without the pull of inertia. Its movement is closer to the effortless drift of light reflections on water than to the motion of any solid object. If you have ever watched a beam of sunlight filter through dust particles in a quiet room, you can almost sense the contrast. The dust particles fall slowly, pulled by gravity, their paths influenced by every small current of air. But the light streaking between them does not fall. It does not drift sideways. It does not hesitate. It travels in straight lines, untouched by the currents that disturb everything else. The dust lives in a world of mass. The light lives in a world beyond it. The idea that something can have no mass might feel abstract, but the consequences are simple and profound. It means a photon cannot resist motion, because resistance requires mass. It cannot accumulate inertia, because inertia is mass. It cannot ever be at rest, because rest is only meaningful for objects that can choose between stillness and movement. The photon is always moving because its very nature depends on movement. If you picture a leaf falling through the air, you see mass at work. The leaf drifts, turns, slows, and eventually touches the ground, carried by the push and pull of forces. A photon, by contrast, is like a leaf made entirely of motion. It does not fall, it does not drift, it does not settle, it exists as pure travel. not because it is trying to reach a destination, but because travel is the only state in which it can exist at all. This constant motion is also why photons can cross such vast distances without losing their identity. A photon from a distant star may travel for thousands or millions of years before reaching your eye. During that entire journey, it does not slow or fade. Its lack of mass allows it to maintain a perfect, unwavering pace through the emptiness of space. Every moment of its existence is motion, and every moment of that motion is identical to the last. There is something wonderfully serene about this. A photon begins as a quiet disturbance, travels across the cosmos without effort, and ends by giving all of its energy to whatever absorbs it. It is a life lived entirely in transition, entirely in motion, without any of the complications that come from having mass. It does not struggle or strain, it simply moves. Understanding why photons have no mass turns them from mysterious entities into elegant ones. Their freedom from mass is not a flaw or a limitation. It is the very thing that allows them to carry the warmth of the sun across space, to illuminate your world and to reveal the colors and shapes that fill your life. Their masslessness is not emptiness, it is possibility. It is the quiet grace of energy moving as simply and beautifully as nature allows. If you watch cars on a road or birds crossing the sky, you notice something simple about motion. Different things move at different speeds. A car accelerates from a stop, gathering pace little by little. A bird might take off slowly, flap harder, and then glide. Even water flowing down a river can speed up or slow down when the terrain changes. In everyday life, nothing moves at a fixed, unchanging pace. Everything that has mass must work for its motion, and the speed it reaches depends on how much force it receives and how much resistance it encounters. Light does not behave this way. A photon does not begin slowly and pick up speed. It does not push against anything. It does not build momentum. It does not accelerate the way a thrown ball or a falling leaf does. Instead, a photon comes into existence already moving at the fastest speed the universe permits. It is created in motion and stays in motion for as long as it exists, without ever slowing down, without ever changing pace. This strange behavior is not caused by the photon itself. It is a property of the universe. The structure of space-time, this quiet, invisible fabric that shapes the rhythm of distances and durations, sets the speed at which ripples in the electromagnetic field can travel. That speed is not decided by the photon. It is built into reality. One gentle way to imagine this is to picture the universe as a vast, calm ocean once again. The surface of that ocean has a natural speed at which ripples can move. You cannot persuade a wave to travel faster than the water allows. You cannot shout at it or push it or plead with it. The wave simply moves at the inherent speed defined by the water's properties. In the same way, a photon travels at the speed set by space-time itself. This cosmic speed limit is woven into the very geometry of the universe, the same geometry that tells clocks how to tick and rulers how to measure distance. When a photon is released, whether from an excited atom, a distant star, or a spark in a firefly, it appears in the electromagnetic field, already travelling through space-time at this fixed pace. No warm-up, no acceleration, no hesitation, just immediate, perfect motion. Because photons have no mass, nothing slows them. They feel no inertia. There's no weight to anchor them, or friction to diminish their journey. They skim across the universe with astonishing consistency, following the contours of space-time like a dancer following the shape of a melody. Even when gravity bends their paths, it does not reduce their speed. It simply guides them along a curved trajectory. To make this idea even more intuitive, picture walking on a moving walkway at an airport. No matter how lightly you stroll, the walkway carries you forward at its own steady pace. You can choose to walk faster or slower relative to the walkway, but you cannot change the speed at which the walkway itself moves. A photon has no option to stroll or sprint. It is carried completely by the movement allowed within space-time. It does not choose its speed any more than a ripple chooses the speed at which it spreads across a lake. This has a curious consequence. To a photon, time behaves differently than it does for you. Photons do not age. They do not experience the passing of seconds or the slow accumulation of moments. From their perspective, if such a perspective could exist, their entire journey begins and ends instantaneously, whether they are traveling across the width of a room or across a galaxy over millions of years. They are creatures of pure motion, and motion at this extreme pace reshapes the meaning of time itself. Einstein's theories of relativity help explain this phenomenon, though we can explore it without diving into heavy mathematics. In relativity, time and space are linked. When something with mass accelerates, it uses energy both to increase its speed and to reshape how time flows for that object. The closer it gets to the cosmic speed limit, the more difficult it becomes to accelerate. It is like trying to run through deep water. The harder you push, the stronger the resistance feels. Objects with mass can get close to the speed of light, but never reach it, because doing so would require infinite energy. A photon faces none of this. Because it has no mass, it does not need to fight through any resistance. It does not need energy to accelerate. It has no inertia to overcome. So it simply exists at the one speed the universe allows for massless particles. This speed shapes so much of what you see and feel. When sunlight reaches your skin, it has traveled across nearly 100 million miles at this fixed pace. When you gaze at stars, the light entering your eyes has been traveling for years, decades, centuries or more. And yet, no matter how far it has come, the photon has never slowed. It has maintained the same speed every moment of its existence, running through space-time along a perfect, unbroken path. There is calm certainty in this behavior. The universe is often unpredictable, but the speed of light is one of the rare constants that never wavers. It is the same in every place, at every time, for every observer. Whether you are moving toward the source of light or away from it, the photon still travels at that same cosmic pace. This stability becomes a kind of anchor for physics, a quiet rule that helps shape everything from the structure of atoms to the expansion of the universe. Think of space-time as a vast stage where many performances unfold at once. Some actors move slowly, some sprint, some drift lazily, or curve gently around unseen gravitational wells. But photons glide across the stage at a speed no one else can match, following the single tempo set by the universe itself. Their pace is not personal, it is structural, it is determined by the very stage beneath their feet. The fact that photons always travel at the speed of light is not just a fascinating detail about how light behaves. It is part of the deep symphony of nature, one of the harmonies that keeps the universe coherent and connected. It ensures that warmth and color can cross space, that information can travel from one point to another, that stars can shine across cosmic distances, and that your eyes can turn those tiny pulses of energy into images and meaning. It is difficult not to feel a sense of peace in that thought. Light is steady, light is reliable, light moves with the same unwavering pace through every corner of the universe, whether crossing the space between atoms or the emptiness between galaxies. Photons do not rush, they do not tire, they do not vary their speed in moments of stress or calm. They follow the rules of space-time with quiet precision, carrying energy in the simplest, most elegant way possible. When you imagine a photon traveling across the universe, picture not a frantic race but a serene glide. Picture a ripple moving across the most tranquil sea imaginable, smooth, effortless, unchanging. That is how light moves. That is how photons exist, and that is why every sunrise, every starlit night, every flicker of a candle is made possible by a pace set not by the photon, but by the universe itself. If you imagine an atom as a tiny solar system, with a dense nucleus at the center and electrons moving in delicate layered orbits around it, you're already most of the way toward understanding how photons come into being. The details are different from planets and moons, of course, but the broad idea helps. Electrons do not wander freely. They occupy specific energy levels, almost like steps on an invisible staircase. And those steps are precise. An electron cannot float somewhere between them in a casual mid-air pause. It must be on one step or another. Now electrons are restless creatures. They are constantly nudged by energy, from heat, from collisions, from electric currents, from the warmth of starlight drifting through space. When an electron absorbs just the right amount of energy, it can leap from one step to a higher one. Think of it as climbing a rung on a ladder. But this excited state never lasts long. The universe prefers stability, and electrons quietly agree. So after a short moment of excitement, the electron slips back down to a lower energy level. When it does, the extra energy it no longer needs does not simply vanish. Nature never throws away energy, it transforms it. And in this case, the transformation is simple and elegant. The atom releases the leftover energy into the electromagnetic field as a tiny pulse. That pulse is a photon. This moment is so small and so fast that it is difficult to picture, but you can imagine it as a quiet flick of light emerging from the atom's interior, a gentle shimmer slipping away into the surrounding space. It is not a spark in the fiery sense. It is more like a whisper of energy, leaving the atom with absolute precision. And because the atom releases a very specific amount of energy, a difference between the two steps of the invisible ladder, the photon carries exactly that amount, not more, not less. A photon is, in effect, the perfect envelope carrying the exact change from the electron's transition. This is why photons have different energies depending on how they are created. If an electron falls a large distance between energy levels, the photon it releases is more energetic. If the step is smaller, the photon is gentler. Your eyes detect these differences as colors. Photons with higher energy appear as blues or violets. Lower energy photons arrive as reds. Everything in between paints the world with the colors you see each day, but electron transitions are only one of the ways photons come into existence. Nature has a wonderfully generous habit of producing them in many situations. Whenever something is warm, even slightly warm, atoms inside it vibrate and jiggle. Those tiny motions cause electrons to move in subtle ways, releasing a steady stream of photons. This is why everything above absolute zero emits some amount of light, even if most of that light is in a wavelength you cannot see. A hot stove glows red. A piece of metal heated in a forge glows orange, then yellow, then white. Each glow is the language of photons, spoken through temperature. Starlight is another source, perhaps the most poetic one. Deep within a star's core, atoms are squeezed together so tightly that they fuse, releasing vast amounts of energy. That energy drifts outward, hopping from atom to atom in a process that can take thousands of years. Eventually it reaches the star's outer layers, where countless electrons shift, settle, and release photons that escape into space. Some of those photons travel across unimaginable distances and end their journey in your eyes. The soft twinkle of a star is not the star itself. It is a stream of ancient photons finally completing their long journey through space-time. Chemical reactions also produce photons, including some you may have seen without realizing it. When something burns, for example, the rearrangement of atoms causes electrons to jump between energy levels, releasing photons as part of the process. Flames glow because electrons are busy leaping and settling, constantly sending out small packets of energy. Even the gentle spark from two flints striking each other is a flurry of photons being released from atoms jarred into excited states. And if you have ever watched a firefly in the summer, blinking softly in the evening air, you have watched a living organism orchestrate chemical reactions specifically to create photons. A firefly's glow is nature performing its own tiny symphony of transitions. One of the most charming things about photons is how quietly they begin. There is no violent kick, no dramatic explosion, no miniature trumpet announcing a new particle's arrival. A photon's birth is serene. It is a rearrangement of energy, a small difference being released with perfect accuracy, a delicate pulse slipping into the electromagnetic field as gracefully as a breath of air. You can imagine an electron releasing a photon the way a harp string releases a note. The string vibrates, the note escapes, and both settle into stillness afterward. The photon carries a tiny piece of the atom's energy outward, moving at the speed of light the instant it appears. There is no warming up, no gathering momentum, just an immediate transition from stillness to motion. And if you like a moment of gentle humour, you might imagine electrons as fidgety musicians who cannot resist plucking at their strings. Every time they settle down after absorbing energy, they send another shimmering note into the universe. The symphony never ends. Every star, every warm object, every living thing contributes its own tiny melody of photons. The universe is constantly glowing, singing in packets of light, even if your eyes can hear only the smallest part of that song. The most beautiful part is that these photons, born from such delicate changes, become the foundation of sight, warmth, and life. A single photon released deep within a star might travel for millions of years before brushing against your skin or slipping into your eye. A photon released by a leaf may help another plant recognize the presence of sunlight. A photon emitted by your phone screen may be the one that shows you a message from a friend. Each one is a tiny carrier of energy, a messenger without mass, a flicker of information that began with a simple rearrangement inside an atom. The creation of photons is not dramatic, it is not forceful, it is not violent, it is gentle, precise, and constant. Energy shifts, and light is born. A ripple begins in the electromagnetic field, and the photon's journey unfolds. By the time it reaches you, it may have crossed distances so enormous that the human mind struggles to imagine them, yet the photon itself remains unchanged from the moment of its creation. And so, every beam of light, every warm glow, every spark, every gleam in someone's eyes begins with a tiny rearrangement inside an atom. A small shift, a quiet release. A pulse of energy that slips into space, ready to travel the universe with perfect grace. Colour feels like one of the most familiar parts of everyday life. You open your eyes in the morning, and the world greets you with soft blues, quiet greys, warm yellows, or whatever palette the sky has chosen for that particular moment. You pick up fruit and notice its ripeness through hints of green or red. You recognize friends by the colors of their clothes, their hair, their eyes. And yet, beneath all this comfort and familiarity, color is simply the story of photons carrying different amounts of energy. That is all. What feels like a sweeping canvas of hues and shades is really a spectrum of tiny pulses of light, each one arriving with its own distinct energy, its own soft signature. When an electron inside an atom settles into a lower energy level and releases a photon, the exact amount of energy it lets go determines what kind of photon appears. If the energy difference is large, the photon is more energetic. If the difference is small, the photon carries less energy. These small variations create the entire rainbow. Higher energy photons are seen as blues and violets. Lower energy photons arrive as reds and oranges. Everything in between glows with the colors you see woven throughout the world. This means that color is not a coating on objects or a dye in the air. It is not something painted onto the surface of the world. Color is a message. It is a whisper of energy carried by photons that your eyes translate into sensation. The blue of the sky is the result of photons scattered by air molecules. The deep red of a sunset comes from sunlight, passing through a thicker layer of atmosphere, where the lower energy colors slip through more easily. The green of a leaf emerges from photons that plants reflect after absorbing other colors to power their chemistry. What you call color is really your brain's interpretation of light's energy, a quiet collaboration between physics and perception. To understand this gently, imagine holding a prism up to a beam of sunlight. The white light, which appears so plain at first, spreads into a fan of colors. Each color bends slightly differently because each color's photons carry a different amount of energy. The prism does nothing magical. It simply reveals what was always hidden within the light. Every ray of sunlight contains a spectrum, a blend of energies layered over one another, and your eyes are exquisitely tuned to interpret those energies. But while your eyes can detect colors beautifully, they do not see the full range of energies that photons can carry. Some photons have too little energy for you to notice. These are the gentle, comforting photons that warm your skin on a cool day. Others carry far more energy than your eyes can handle, slipping into the realms of ultraviolet and beyond. These high-energy photons can affect living cells, which is why sunlight both nurtures and challenges life. So the colors you see represent only a small portion of the full symphony of light. Your eyes hear a few notes, while the universe plays the entire score. This connection between energy and color becomes even more beautiful when you look beyond Earth. Stars, for example, are natural factories of color. A star's temperature determines the energy of the photons it emits. Cooler stars glow in deep oranges and reds, like embers resting in the hearth of the cosmos. Hotter stars shine in brilliant whites and blues. When astronomers look at starlight through their instruments, they can read the rainbow of energies within it and learn a star's temperature, age, chemical composition, and even how fast it is moving. In that sense, starlight becomes a letter from across the universe written entirely in color. Nebulae offer another kind of cosmic artwork. These vast clouds of gas and dust glow when they are illuminated by nearby stars. Hydrogen emits a soft, rosy red when excited. Oxygen glows in shades of cool teal or pale green. Sulfur radiates in gentle red tones. When photographed through special filters, nebulae appear like enormous swirling paintings suspended in space, each stroke defined by the photons escaping atoms light years apart. The colors do not come from pigments or dyes. They come from electrons jumping between energy levels and releasing photons with precisely defined energies. And yet, for all this scientific precision, color feels emotional and intimate. A warm golden sunset can make you feel calm. A cool blue morning can bring a sense of clarity. A forest of green can soothe your mind. These feelings arise not just from the physical properties of photons, but from the way your brain has evolved to interpret their energy. Humans have built entire languages around color, symbolism, art, expression. Yet at the heart of it all lies a simple fact. Color is energy, arriving in tiny packets, transformed by your mind into meaning. In a way, color is where physics and emotion meet. A photon does not carry a preference for beauty. It does not know that it will paint the sky or give life to a field of flowers. It simply travels, carrying energy across space. But when that energy meets your eyes, it becomes something more. It becomes perception. It becomes mood. It becomes memory. The same photon might warm your skin, grow a plant, or reveal the shades of a rainbow. It is astonishing how much can come from something so small. Perhaps one of the most calming thoughts is that the colors you see every day are part of a larger cosmic palette. The soft blue glow of Earth's atmosphere, the warm gold of the sun, the deep reds of distant stars, the ghostly purples of nebulae, each one is written in energy. When you look up at the night sky, you are seeing photons that began their journey long before you were born, carrying their colors across unimaginable distances. Some may have been created in events older than human history, drifting patiently through the darkness until they reach your eyes. Color becomes a gentle reminder of how connected you are to the universe. The photons that paint the world around you come from electrons shifting within atoms, or from heat radiating outward, or from stars burning far away. Each one carries its own energy, its own hue, its own message. When they arrive, your eyes read those messages without a single conscious effort. You're constantly decoding the universe without realizing it, interpreting the quiet language of energy. And so, when you look at the world, you can think of every color as a signature, a unique imprint of energy carried by a photon on its journey through space. Reds whisper of warmth and low energy. Blues speak of higher energies and sharper transitions. Greens arise from the delicate balance of photons reflected by the living world. Even the colors you cannot see, the infrared warmth of a quiet room or the ultraviolet glow hidden in sunlight, play their part in shaping your surroundings. Color is more than light. It is the universe communicating through energy. It is physics expressed as sensation. It is the soft translation of quantum behavior into something gentle, vivid, and beautifully human. When you first hear that photons behave like both waves and particles, it can sound like someone is trying to have two completely different ideas at the same time. A wave is something that spreads, soft and continuous. A particle is something small and concentrated, arriving in one place at one moment. How could a single thing possibly behave as both? It feels like being told that a whisper can also be a pebble, or that a ripple on a pond can also be a droplet thrown into the air. But in the quiet world of quantum physics, this dual behavior is not a contradiction. It is simply the way nature expresses itself at its smallest scales. One of the gentlest ways to approach this idea is to remember that the universe does not owe us simplicity. It does not build itself according to what feels intuitive. The way things behave on everyday scales, balls bouncing, water flowing, shadows forming, does not necessarily reflect how nature behaves at the level of its most fundamental ingredients. The quantum world has its own rules, shaped not by intuition, but by the delicate structure of reality. And photons, being among the simplest quanta of all, reveal those rules with remarkable clarity. It helps to begin with the wave-like side of a photon. When a photon travels, it does not move like a tiny bullet fired from a microscopic slingshot. Instead, it spreads out. It moves as a gentle disturbance in the electromagnetic field, occupying a region of space rather than a single pinpoint location. You can imagine it as a soft ripple expanding on the surface of a perfectly still pond. The ripple is present across a wide area, yet it remains one ripple. It does not split into fragments just because it stretches across space. The photon is similar, one entity, existing in a way that feels more like a wave than a bead. Because of this wave-like character, photons can interfere with themselves. If you send light through two narrow slits and watch how it spreads on the other side, you see a pattern of bright and dark stripes. It looks exactly like the kind of interference you get when overlapping ripples on a pond strengthen one another in some places and cancel each other in others. The strange part is that this happens even if you send the photons through one at a time. Each single photon seems to behave as if it passes through both slits simultaneously, interfering with itself in a way that defies everyday logic, yet follows the rules of quantum physics perfectly. But despite this smooth, ripple-like behavior, photons also behave as particles. When they are absorbed, they deliver their energy in one clear, concentrated package. A photon never arrives halfway. It does not spread its energy out gently over an area. It arrives all at once, like a tiny tap on a sensor in your eye, or a small packet of warmth landing on your skin. Even if the photon had been spread across a wide region of space moments before, the instant it is detected in one location. The entire ripple collapses into a single, definite absorption event. This duality, spreading like a wave, arriving like a particle, is not something scientists invented to confuse anyone. It is something they discovered when they finally learned to look closely enough.